Okay, gonna go over a couple things for anatomy and the things that we've been learning for this unit so far, mainly just kind of some anatomy and structure of the heart. We're gonna talk about how action potentials carry out the different types of cells that are in AV and SA nodes. So the SA and AV nodes, they're gonna have more like nodal cells. They can kind of spontaneously contract on their own. And then we have the contractile cells, and we'll talk about those. And so we got a lot to talk about, but I'll try to be really quick. Okay, so first thing I want to do is I am going to use a couple notes here just to look at, okay? So the first thing I want to do is talk about heart action potentials. Okay, heart action potentials. Hopefully we can read that. Yeah, cool. All right, so with heart action potentials, first thing I kind of want to do is go over some heart anatomy. Cool. So we have the heart, right? We have the heart. Something really interesting about the heart is we're going to kind of divide this up into basically 4 quadrants, okay? We're going to have the right atrium, okay? Then we're going to have the left atrium. Then we're going to have the right ventricle and the left ventricle. Now, some of you might be thinking, hey, why is it on the opposite side if it's left and right? Well, you got to think that we're looking at the heart this way, and we got to turn it, put it inside of us. So this is left and right, but when you pull it out and you look at it, that's the right, that's the left. Okay? Cool. So we have a couple structures coming in here that we need to know about. In here, we have this structure called the inferior vena cava, or superior vena cava, and then we have this inferior vena cava come from the femoral artery or femoral vein and those things. So this is the inferior, this is superior vena cava, this is inferior vena cava. Coming in, dropping blood into the right atrium. Now in the right atrium we have something called AV node. And what happens is this will depolarize. It also has this path that can cross over here, so the atrium can depolarize at the same time, and this is going to be called the Bachmann's bundle. Okay, then this can travel down, and then we stimulate this, the SA node. Sorry, this is the SA node, this is the AV node. Okay. And then this travels down here to what we call the bundle of His. We're going to explain how this action potential works in the cells. These up here, these are going to be our nodal cells. Okay, and then these down here, these are going to be our contractile cells. Okay. So we have our SA node, AV node, and we have right and left atrium and those things. Perfect. Okay, so one thing that we also want to know is coming out of this spot here, coming out of here, okay, we have the aorta coming out of that left ventricle. Okay, cool. So right here at the bundle of His, we then would have our left branch bundle branch. Okay, and then we have over here, we have our right bundle branch. Okay, let me make sure I got everything. Yeah, the SA node is also known as the pacemaker, so we want to make sure that we know that. I got everything. Other thing is AV node is going to be about 0.1 seconds behind the SA node, okay? So that's important to remember and know because the atrium is going to contract before the ventricles are going to contract. Yeah, I think I got everything. We just have the intraventricular septum right here. Inter meaning between, and then ventricular in the ventricle, and then septum meaning that canal crack there. This is going to be the apex. This will be our base of the heart. So refer to the base, referring to the top, refer to the apex. It's going to be down low. Okay? Cool. There's two vocab words we kind of want to know with this. We want to know automatricity. This means that the heart has the ability to create its own, autonomic rhythm, and so it can depolarize on its own. It doesn't need to go through, T-tubules and those kind of things. We have these HCN funny channels. We'll talk about those. And so the pacemaker can kind of depolarize spontaneously on its own. It's not controlled, okay? And then we have ectopic foci. Okay, and then this is just where the pacemaker cells, they're going to grow out of place. So when they're not in the right spots, then we have ectopic foci. Okay, ectopic, kind of like an ectopic pregnancy, something growing where it's not supposed to. That's what happens with children with birth sometimes. Okay, so one thing that we want to know with this is we kind of want to know how this works in a cellular level here. Okay, so that's going to be my nodal cell, and this one right here, this is going to be my contractile cell. Hopefully we can see those. Perfect. So one thing that I want to do is I want to label these. I want this to be my nodal cell. Okay, and this is going to be a contractile cell. Okay, so what we end up having is we have this channel on the membrane here called HCN, and we call it a funny channel. Now on the graph that we use in the textbook, this is also going to be called a INA channel. Okay? No, these are ligand voltage gated channels, but this is called an IF channel. Okay, IF channel. Perfect. So an IF channel, what's really important about the IF channel is this is going to allow sodium to come in. This depolarizes the cell, and then this is going to activate a channel up here called a calcium channel, L and T, calcium channels, where calcium comes in because it's activated from that sodium channel. We also have channels here that get activated. These are potassium channels that will start to have potassium be permeable and leave the cell, and so we get this negative charge. What we have here is we have this polarization, this depolarization that can happen in the cell, and then we have this crossing tube right here between the cells, and this is called the gap junction. Okay, and what ends up happening in the gap junction is that positive charge that was created here, and that depolarization can actually travel over and have an effect over here. So we want to draw this one on a graph right here, okay, and what's happening. So we see if we're at negative 60 millivolts resting membrane potential, what we see is something interesting happening, and that is, if this is our threshold here, we see that this funny channel, HCN, we'll just call this IF right here. This IF channel is going to get us up to threshold. That opens up those calcium channels, so we're going to shoot straight up, right? Those are going to be our L and our T calcium channels, and I believe these are called ICALT channels on the graph. Okay, so that's going to happen there, and then we're going to have this repolarization back down to resting membrane potential, and then we'll kick right back up on the second go around. So this one right here is going to be the potassium channels opening up and repolarizing the cell, repolarization. We don't have any form of hyperpolarization, so we don't have that overshoot occurring in the cell. So what ends up happening is those come out, and those are just going to be called our IK channels. And then the calcium channel would close there. Cool. This one, I'm going to draw this one out on the graph first, and then I'll kind of explain how it works on there. So how this one works is we're at negative 90 millivolts. Okay. And so what ends up happening is we have this action potential that occurs right here. We have this straight line, and then we all of a sudden get this spike that shoots us up. Yeah. So then we're going to have this spike that just kind of shoots us straight up here, and then we're going to come down and kind of plateau, and then we have that repolarization back down to there. Okay. And then we kind of plateau again on the base. So we're going to label these 4, 0, 1, 2, 3, and back down to 4. Can we see that? Perfect. So what ends up happening with this is at 4 we have, you know, these they're called IK1 channels or IKA channels that keep the cell from actually hyperpolarizing. And this one, the sodium channel is actually going to open up. So these are going to be our sodium funny channels. So these will be HCN, but we'll also call these IF channels that are going to open up. I believe that's what I labeled them, INA. I think they're called IF channels that are going to open up right there. Then up here at number 1, we have something happening. We start to repolarize up here. So we have this thing called I2-1 and I2-2 that open up, and this is going to be a potassium channel leaving, and then this will be chloride channel, and the chloride will be coming inside the cell. That's negative, and so we have this repolarization, but then it gets fought a little bit, and so we extend the contraction. So we're going to write here extend contraction. And so what ends up doing this is the potassium is calcium, and so we have these Ca, we have these I, CAL. So that stands for the I, calcium, long. L stands for long, elongated. T will be shorter ones. So L would be our longer. They're longer in terms of the contraction, and then the T would be faster. So we have these ICAL channels that open up, and so what ends up happening is you have that calcium that's coming out, and we have this plateau phase. We call this plateau. Okay, plateau phase. But what ends up happening is you also have an increase in these potassium channels. So you have IK R, IKS, and IK, I believe it's UR or RS. Yeah, it's UR, IKUR. And so they overpower, and so we have this IK1 channel, and we end up repolarizing the cell and overcoming the calcium, and then we come back to IKA, so we don't hyperpolarize. Cool. So what that looks like up here is we're going to have our sodium channel that will be activated. So this would be IF, and that's the funny channel, so that gets activated here, and that stimulates that, so we get positive charge, and then that's going to stimulate our next channel up here, which is going to be our calcium channel, L-gated calcium channel. Well, that doesn't get stimulated yet. This will be our Cl minus that will come in, and then we'll also stimulate at the same time. We're going to have our potassium channel that comes out, and then we'll stimulate our calcium channel here. And when the calcium gets stimulated, we're going to allow calcium to come in. These are calcium elongated channels. Okay, you kind of get the picture. We're going to have this fighting here. This would be the plateau phase. Plateau, and then it gets overcome, and we have all these calcium channels that open up. IKUR, IKS, IKR, and these channels end up opening up, and we have this depolarization that takes place here. And so we have this repolarization back down, and so then we're back at resting membrane potential, so we can have another active potential come through. Okay, so that's kind of how those cells and all that works. Coolio. So I think I'm going to leave this up for something else I'm going to teach on. Chronotropy, inotropy, and lustropy, and EKGs. So something that's really cool that happens here is we have something called positive chronotropy. Okay, and that's going to increase heart rate, and in doing so, it'll also increase the strength of contraction, and so we'll increase strength of contraction, and then we also increase the speed, so it would be tachycardia. Okay, and I'll explain kind of how that works, and then over here we're going to have negative chronotropy. And this is going to decrease heart rate and decrease strength of contraction, and it's going to be called bradycardia. And cardia meaning heart, and brady meaning slow, cardia meaning heart, and tachy meaning fast. Okay? So we have tachycardia, we've got all that going on. So here's something really cool that ends up happening. What ends up happening is, for this is a SNS, sympathetic nervous system, okay? Because we're going to be attacking a beta receptor, okay? So this is what's going to happen. You got the SNS going on. We have a neuron here that's going to release norepinephrine or epinephrine, okay? Then we have a receptor here on the membrane. This is a G-coupled protein receptor, and so this is called beta 1. So this makes its way over, and we end up having a binding ligand gated channel, so then activated. So this is beta 1, so this will then activate, I believe it's an alpha subunit first, and then, let's see, beta receptor adenylyl cyclase. Yeah, so this will activate adenylyl cyclase, and then we get ATP, CAMP, and then protein kinase A. Okay, so this will activate adenylyl cyclase. Then adenylyl cyclase will activate CAMP, because this will take an ATP, put it on here, and so we get cyclic AMP, and then this will activate protein kinase A. Then protein kinase A and CAMP can activate a couple of these other things. So I believe it's more so going to be CAMP that activates the sodium, and then the protein kinase A will activate the calcium channel. So on this membrane here, let's just say we have another HCN. Okay, and this sodium, and so the sodium's going to come in here. That's activated by this CAMP. This CAMP actually excites that to start happening. Yeah. And then protein kinase A protein kinase A will activate calcium alligated channels, and that will activate those. So in all, we're going to get, you know, depolarization, which will increase calcium up here, or we get an increase of ECF calcium, and so this just increases contraction, strength of contraction, increases heart rate. So heart rate goes up, and that's because this can propagate and continue to move in here through the gap junction and actually cause depolarization into the other cell. But this one, that will increase heart rate there, but this one is going to be a little bit different because we're going to have some other things that go on here. But I want to explain how this thing actually gets inhibited as well. So we have negative, right, like I said. So this one has, you know, comes from the PNS, parasympathetic nervous system, and it's going to have its receptor here, and it's releasing acetylcholine, right? So this will be ACH for acetylcholine, okay? And that's going to bind here on the membrane. Again, we have this, you know, G protein couple receptor, but it's unique because it's bound to this alpha, beta, and this gamma subunit complex. And so this will end up breaking up. We'll have our alpha go up here, and then we have our beta and gamma that stay down here. And what ends up happening is we have this thing called the Gurk channel. Gurk channel. Yeah, Gurk plus. Okay, this is going to allow potassium to come out of the cell, so it causes a hyperpolarization. So this could lead to a decrease in heart rate. Okay, so if we want to decrease heart rate, and this is called an M2 receptor. So parasympathetic nervous system, rest and digest, we can decrease heart rate. We can actually do that using this neurotransmitter to activate that beta and gamma subunit to bind to the Gurk channel. Alpha subunit can actually come and inhibit the CAMP, and when it inhibits CAMP, it's going to inhibit this HCN funny channel for sodium. It can also come and inhibit the PKA, which is phosphoryl kinase A, which will in turn come and inhibit the calcium channels that come in. So all in all, that will decrease heart rate and cause the cell to be a little bit more negative if we're not letting in more of these positives. And we call that hyperpolarization. And we're going to decrease contraction strength. But most importantly, we're going to decrease heart rate. Okay. Perfect. So, something I want to draw up over here is kind of how this all gets activated or stimulated. Turns out PNS isn't going to activate this over here, the contractile cells. It's going to be, you know, and these are found more in Purkinje fibers, right? So that's something I forgot to mention over here, but we have these Purkinje fibers, okay? And these Purkinje fibers exist over here, and they're going to make up those cells within the ventricles so that we can have contraction there, okay? So we have on this membrane, we're going to have this G-coupled protein receptor that's here, and it's going to get bound, and we have, you know, this synaptic gap occurring, and we have this release of a neurotransmitter, and so this is norepinephrine, adrenaline, or epinephrine. Okay, and again, this is coming from the SNS, sympathetic nervous system. We also call these catecholamines, okay? So, again, this is a beta-1 receptor, and this is G-coupled protein receptor, so we're going to branch off. We're going to create this alpha subunit. Alpha subunit will then go and activate adenylyl cyclase, which then activates cyclic AMP, which then activates this thing called protein kinase A. Okay? Super important. Okay, this is going to be really important for a couple reasons. Because with inotropy and lesotropy, because that's kind of what I'm explaining over here, inotropy and lesotropy. And this means an increase in calcium, and this is a decrease in calcium. Okay? So the first thing that we can do here is we can activate these, he can come over here and he can activate these. Nope, not those. Come over here and activate these calcium channels. He can turn those on, calcium-gated ion channels, and allow more to come in. What they do is they go to this thing called the sarcoplasmic reticulum. And SR, sarcoplasmic reticulum. And what he can do is he can come over here and he can actually turn on the RYR. And we call this calcium-induced calcium release. Calcium release process. And they bind here, and then we have calcium leaving into the extracellular space. Okay? So when that calcium leaves, we then can have more cross-bridge cycling and increase in contraction. Okay, now PKA can do the same thing. PKA can actually activate these calcium channels, which will then do the same thing. They'll come over here, bind on the RYR, calcium-induced calcium release. We release calcium, and then the calcium is going to be able to come out and do the cross-bridge cycle, actin, myosin, troponin, tropomyosin. We're going to be able to do contraction of the cell. Okay? So we have that. The third thing, so this one's 1, this one's 2. PKA can actually come over here and it can just do it itself. We can turn on the RYR itself right here, and we can let calcium out. And that's also going to be inotropy. So we're going to increase this calcium release. We call it increased contractility, increased inotropy. And then we also have our third or fourth one. So one other one we have over here is called phospholamban. So PKA can actually turn on something called phospholamban. Okay? And phospholamban can come over here to the sarcoplasmic reticulum, and it can turn on the circa pump. And we know that the circa pump will increase its uptake in calcium, take that calcium, and put it back into the sarcoplasmic reticulum. And that could be a problem. That could be a problem because then we're not gonna have enough calcium to bind to the troponin C to then do contraction for us. And so if we don't have enough of that, it makes it hard for the cell to contract. And in this case, it's a heart cell, so the heart cell has a hard time contracting. Okay. So we have a decrease in the plateau phase, decrease in inotropy, but increase in lesotropy. and then increase in circuit pump activity, and again, that's using phospholambin. Okay, so my last one that I want to talk about is going to be, let's see, last one I want to talk about is going to be how PKA can also use lustotropy, and it can actually bind to troponin I. And then this decreases calcium and kind of has it release the calcium. And so it's going to be removed from troponin C. And then once it's removed from troponin C, then we're going to increase relaxation. And we decrease contraction. Or contractility. Okay? So let's run through this really fast. We can have the sympathetic nervous system activate norepinephrine and epinephrine, which can release those neurotransmitters, bind on a beta-1 receptor. The beta-1 receptor will then move up and activate the adenylyl cyclase, which then takes an ATP and creates cyclic AMP, and then we create CAMP. What ends up happening is CAMP can be an excitatory thing to funny HCN channel, IF, sodium channel, which will allow sodium to come in, increasing the overall calcium eventually, which will then lead to depolarization and increased contraction. Then we also have this calcium channel here, which is going to be activated by PKA during this process. PKA opens up that calcium L channel and then allows for calcium to come into the cell, thus depolarizing the cell more, having more leave through gap junction, causing depolarization in the neighboring contractile cell. So all this happens, and meanwhile, that's going to increase heart rate, increase contraction strength, and it's going to increase the speed of which the heart's beating. That's called tachycardia. Then we're going to have this inhibitory response. We have an alpha beta gamma subunit complex. This is going to be activated by acetylcholine through the PNS system. So the acetylcholine will bind to the muscarinic 2 M2 receptor. This will activate the splitting of this alpha beta gamma complex. Alpha is going to go up. It can inhibit CAMP, which will inhibit the funny channel, but it can also inhibit the PKA, protein kinase A, which will inhibit the calcium channel, that elongated calcium channel. So overall, decreasing contraction strength, decreasing heart rate. Brachycardia is what we call that. The other way it does this is it uses that alpha 1 or the beta gamma subunit, which will go down and activate the GERK plus channel, which is a potassium channel, which will allow potassium to be more permeable to the membrane, leading into the ECF, extracellular space fluid, and then we end up having this hyperpolarization occurring, which will make the cell more negative and decrease heart rate and decrease contraction strength, overall being bradycardia. Okay, so that's everything there for that that I wanted to go over, and then I'm going to hit some EKG information right now. Okay, so let me go ahead and erase this, and then we'll hit some EKGs. Okay, EKGs. Super important because this tells us the stages at which the heart will depolarize, okay? So one thing that we want to know about this is we want to know kind of how our leads are set up. Okay, so I call this leads. So we have a positive up here, negative here. Okay, positive here, negative here. This lead right here is called a type 1. Okay, and then this lead here is called a type 2. So we're going to be kind of going off of a type 2 way of thinking in terms of leads. Okay, so type 1, type 2, it's called a Z series, or Z sensors is what we like to call them. Okay, so now I'm going to go over some examples of kind of what we want to know about this. Okay, so for example, you could have your negative lead over here, positive lead over here. We talk about depolarization, it's on the outside of the cell. We're not talking about the cell, but the depolarization on the outside of the cell. So what ends up happening is you have negative here and positive here. We want to know a couple rules when we're determining these for exams and stuff. So negative likes negative on top, okay? Positive likes positive on top. And we got to watch our arrow here of depolarization. So this is saying, or stimulating, or portraying that we're kind of moving this way with depolarization, okay? So let's say we're depolarizing the cell this way. So we erase these here and we make those negative there and we polarize that, okay? This, in terms of its graph, is going to look like this. We're going to look like this. We're just kind of depolarizing a little bit, okay? Then we can have a graph that we can have one looking like this, okay? And this would be a half depolarization. Okay, and we can also have one that looks like this. And we have our negative lead here and our positive lead here. So if we look at this, we have negatives here and it's 3/4 of the way, so then it would look like this, almost fully polarized there. And then if we wanted the full shebang here, we would have it like this, or we could have one. Whoops. Fully depolarized on the outside of the cell, negative loves negative, so then we end up having full depolarization. Okay, so we can mix this up a little bit, and we can say, oh, and let's just pretend all these arrows are going this way, right? So we can make this up a little bit, and we can say, all right, well, what if we switch the arrow around, Hunter? So let's go. Let's just say negatives over here, positives here, but we're going to pull the arrow this way. And let's say we had, you know, positive, positive, negative, 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 and negative, 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 positive, positive, positive. Well, if we're going this way and it's negative, then this is going to flip upside down because it's not on the right side. So this ends up looking like this. And it's halfway, because it's halfway, so it flips upside down. Okay? So we can go over a couple more examples of that, but that's kind of where we're going with why we care about these EKGs and kind of what's being stimulated, what's not. All right? So outside of the cell propagation, so one thing we want to know is kind of what's going on. So we're going to talk about depolarization and then repolarization. So what ends up happening is depolarization, we're going from epi to endocardium, or endo to epicardium. So inside, outside, endo to epicardium. And on the repolarization, we go from epicardium to endocardium. Okay? So what ends up happening is we have a couple things going on here. First thing I want to do is talk about where we're going here. So we're going to go from the SA node, and that will depolarize, and then we're going to have the AV node depolarize, and then we go through the Bachman's bundle. Well, that happens up there, but we go through this thing called the bundle of His, and we depolarize the ventricles, and then which are the Purkinje fibers. Right? Okay, so an example graph of this that we want to know is this. This is a normal heartbeat on an EKG. So right here, we have our P wave, then we have our Q wave, and our R wave, and our S wave, and our T wave. Okay, and I'm going to explain what each of those mean. So let's start with our P wave. So our P wave is going to be pointed down. This is negative up here, right? And this is positive here. That one's pointed down, and this is going to be the depolarization of the atrium. And we do Bachman's bundle, and it's a simultaneous depolarization that occurs. Okay? Then we have the Q. Okay? And Q is kind of pointed like this with its arrow. Okay? So slightly up. And Q is going to be the depolarization of the superior septum. Pretty sure that's right. Superior septum. Okay. Then R is huge, and that's going to be the arrow is going to be down like this, positive here, and this will be the depolarization of the inferior septum and the both ventricles. And that's both atrium. Okay, so both ventricles get stimulated there, and so left or right will go first. Right goes before left. Because it's smaller. And this is also going to activate those Purkinje fibers. P, Q, R, S. S is going to be like this. Up. Positive here. It's the depolarization of the supralateral ventricle. Yep. Superlateral ventricular wall. Okay. Superlateral, the depolarization of the superior lateral ventricular wall. Okay. And then we have and that's the last one, so that's this. And then we have T. Positive here, and this one's going to be going up like such, like that. Perfect. So then we have that one going up just like that. And so what ends up happening with here is this the repolarization phase. And if the heart's doing what it's supposed to, we're going to go endo, epi to endo, cardium. So this way we repolarize in reverse. Okay. Cool. Well, I think that's everything for that part there. I did want to mention something about cardiac muscle contraction. Maybe I can do that over here. So what we end up having is we can have cardiac muscle contraction. And if I drew in like a T-tubule here as T-tubule. And what can happen here is you have, you know, the muscular junction, skeletal muscular, or the muscular junction that occurs there with action potential at the passing of, you know, calcium and vesicles releasing and then binding to the N2 receptors, or N1, and then they're going to come down propagation of sodium potassium channels. Well, there's a calcium channel that's right here, and this will come in. We have our sarcoplasmic reticulum, right? And so it can bind here on the RYR and open up calcium, release calcium induced channels, and we can allow calcium to be released here. We do the cross bridge cycle, okay, where we, you know, do our actin, myosin, troponin with calcium, okay, troponin C, move it to pull myosin out of the way, so then the myosin head can bind with actin, and we can do, you know, cross bridge cycling with phosphate being kicked off, and it will contract, and then we'll add ATP and release, then we'll hydrolyze it, and we'll caulk it, and then we'll you know, allow the myosin head to bind to the actin, that releases the phosphate, that pulls it down. So we got the cross bridge cycle going on. Then troponin C can kick calcium off over time, and then two things can happen. Calcium can go back into the sarcoplasmic reticulum here through the sarcopump, but it can also leave through this other channel called a sodium calcium channel. Let me see what the real name is for it. Hang on, there's a real name for this thing. Probably important to know. Calcium exchange channel with sodium. Looks like it's what it's called, and so calcium and sodium leave, so you get 3 sodium that come in, and you get 1 calcium that comes out. To get that back into the ECF. And so if you mess with that, you can have prolonged contraction and change that. So this is muscle contraction. Neuromuscular junction. Okay. So I'm gonna move on to a little last piece of information here. So we got the T wave flipping, and we got the end STEMI and STEMI that I'm gonna explain here really quick. So we have a T wave, EKG abnormalities. Abnormalities, okay? So we have T wave abnormality, we have something called N STEMI, and then we have something called STEMI. Okay, so a T wave inversion, what ends up happening here is you get O2 hypoxia, okay? So if you had your heart like this, and this was our negative and this is our positive, and we divide this into our 4 quadrants, we're here in the ventricle, you would have this death of tissue of cells here, and we call this hypoxia, which is low O2. So it leads to low ATP production, which leads to low ATPase, which then also leads to low muscle contraction. And it also leads to this opening of this potassium channel, which is called the IK-ATP channel. And ATP normally holds it shut, but then it can release it, having no ATP, and so we have an increase in potassium leaving the cell, and then this leads to repolarization. And so we end up mixing it up because we want to go endo, we want to go epi to endo. And what ends up happening is we go endo to epi. And we have the death of these cells here because of that. And so we have this fast repolarization that occurs because of this hypoxic state. And so this is typically happens because you have your aorta coming out here. Well, the aorta has these coronary arteries that feed the heart, and so sometimes you can get blockage here, which decreases the amount of blood that gets here. If the endo's the furthest in and epi's furthest out, epi's going to get fed, but endo won't, and so we have that death of tissue of cells, and we have that low ATP, low oxygen, hypoxic state, hypoxia. Okay, so we have a graph to describe this, and you can see this in a clinical setting of what's going on. And so you would have your normal EKG, P, Q, R, S, T, and then you would raise up. Well, sorry. And then your T would just be inverted. And that's because you're going positive to positive. And so we flip it. Okay, so then we have N STEMI. How N STEMI works is this is just a same kind of deal here. We have our 4 quadrants. We have this depth of this tissue here. Could be a blood.